In this video, I'll introduce you to finding area bounded by curves and the different types of problems you'll see. First, recall that area for rectangles is just height times base. And that's really all we're doing underneath curves as well. If you recall rectangular approximation method, we're basically looking for the height times the width, and we take the limit as n goes to infinity, and so delta x goes to 0, and we're left with the integral, which is still really the height times our width. So for area bounded between two curves, it's simply going to be the upper curve minus the lower curve, because that will be our height, which we'll say is f of x minus g of x, provided f of x is greater than g of x on that interval. We're going to look at 4 examples. We're going to look at an easy example, between two curves, where upper and lower switches, and then a sideways. In other words, we'll have things in terms of y. So here's our first example. We're finding the area bounded by y equals x squared plus 4 from 1 to 4. So the first thing we're going to want to do is draw a little sketch so we have an idea of what this looks like. So there's our graph. We'll approximate that to be 1, that to be 4. So we're simply looking in that region right there. And what I like to do is I like to look in that region and just take a slice. And when I take my slice, I'm taking my slice perpendicular to the x-axis to show that my thickness is dx, meaning I'm integrating with respect to x. So we'll set up our integral with our bounds from 1 to 4. Notice they're in terms of x. And then it's just our function, which is simply x squared plus 4. And if you think about it, there is a lower function, which is y equals 0, so we can say minus 0, and then our thickness is dx. From here, we simply integrate, so we'll have 1/3 x cubed plus 4x, and we can evaluate that from 1 to 4, and in doing that, we'll simply end up with an answer of 33. In our second example, we're going to look for the area between two curves. So for y equals ln of x, we have to remember what that looks like, and we'll just do a rough sketch here, something like that. And let's label. You do want to label your graph because you can mix up, what is upper and what is lower. And then y equals x minus 2, I'll say, is this graph right here. It appears at the end it's above, but again, we're looking for that shaded region. And the other thing I want you to notice is that it's located in both the negative and positive sides of y. That doesn't matter because our upper and lower will always yield a positive value when we have the upper minus lower. So don't let that bother you at all. We are going to need the boundaries that hold this area, and we're going to want those x values. So in this case, you'll need a graphing utility or some other function to be able to find that. And in doing so, we'll find that our first x, we'll say x at a, is approximately 0.1585 and so on. And then our x value at the b is approximately 3.146 and so on. And our integral is very simple then. It's really from the a value, 0.15, so on, to the b value, 3.14, so on. And then our upper, remember, I'll go back to our diagram, is ln of x minus our lower. Now be careful in subtracting your lower limit. If you leave it x minus 2, we're going to have a problem. It's the entire function, so we need parentheses around that because we'll need to distribute the negative, and we'll have dx, our thickness. Now, typically you use a graphing calculator or some other program to solve this. We can look at part of this by hand, but we'll need to know how to integrate ln of x. If you learned integration by parts, you'll already know this is x ln of x minus x, which is a little involved. And then we'll be subtracting what's in the parentheses, our x minus 2, which is simply 1/2 x squared. And then we're going to have minus 2x, and then we'll have to distribute that negative. And again, we'll be evaluating it, and I'll just say it's from A to B. And when you work that out or use your calculator, you'll end up with approximately 1.94909 and so on. In our third example, we're going to see where limits of integration can change. Now, you'll notice our first function, y equals x cubed minus 4x, maybe not so easy to graph unless we put it in factored form, and in doing so, we'll see y equals x squared minus 4. So we're going to have zeros at x equals 0 and plus and minus 2. So we'll just mark those there. And then graphing y equals 5x is just going to be a straight line, but finishing our curve for our cubic, we'll have something like this. We should remember how to do that. And then for 5x, we'll do that. It goes through 0, and we know it's a positive slope, so we can just sketch it like that. And again, we'll need the points of intersection for those areas that are bounded. Notice in this first area I have here that the upper bound is the cubic, and in the second area we have the upper bound is the linear function. So we're going to want to be very aware of that. So again, I'm going to label these up here, x cubed minus 4x and 5x. And we'll go ahead and set up our integral now. So the first half is going to be from that lower bound that we'd have to find, and you would find that that value is at -3 here. Remember, that's the x value because it's dx. And I should show my little slice here and our slice here so we can see how it changes. And that's going to be up to the 0. And then we're going to have x cubed minus 4x. And we're going to be subtracting 5x. And we can put them both in parentheses to be safe. And then we're going to add to that our second integral, which is from 0 to 3. And now our upper is 5x. And again, I could put parentheses there, but our second one is where it's necessary, x cubed minus 4x, and that will be with respect to x. Now, some of you may notice that we could also use symmetry here to realize that those two areas are the same. That will work in those cases where we have something that is symmetrical. Otherwise, we have to be very careful to do all the workout. And in doing the workout, you'll find that we just simply end up with evaluating 1/4 x to the 4th minus 9/2 x squared, and that's going to be from -3 to 0. So that's for our first one. Plus, we're going to have our next integral, which is going to be from 9/2 x squared minus 1/4 x to the 4th. And that will be evaluated from 0 to 3, so you can see the symmetry there. And when you finish evaluating that, you're going to have 20.25 plus 20.25, so you'll be left with a final answer of 40.5. In our final example, we're going to look at something that goes a little sideways, we can say. So the first thing we'll look at is x equals y squared, which some people may feel more comfortable looking at it as y equals plus or minus root x, and that's where the problem lies, because that is no longer a function, so our upper and lower are the same function. And then when we look at y equals x minus 2, we'll say something like this, and there is our region. So our region has an upper and lower of the same function, which we can evaluate, and then it switches to the line and the equation. So I will label this as x equals y squared, and our other function was y equals x minus 2. So what we're going to do instead is we're going to take a horizontal slice. So when I do that, I'm slicing it from right to left because that is my larger value. So now I'm going to be doing the right bound minus the left bound, which means our thickness is delta y or dy. And that means we're going to be summing up from a lower y value, no longer the x, to the upper y value. That dy tells me everything is in terms of y. So in setting up my integral, we're going to have the integral from -1 to 2. We'll have to find those points of intersection, a little algebra involved there, and we'll have that. And our right value has to be in terms of y. It says y equals x minus 2, so I need to change this to solve for x and have what x equals y plus 2. Now I can enter that in as y plus 2. And I will subtract the left side, which is already in x equals form. So we have y squared and dy. And in integrating this, you would see you would just have 1/2 y squared plus 2y minus 1/3 y cubed. That's going to be evaluated from -1 to 2, so we can plug those in and get our values. You'll end up with a final answer of 4.5. Now, here's an odd question for some people. They wonder, can they enter this into their calculator if they only have x? Your calculator doesn't distinguish between x and y, so yes, you can go ahead and do this on your calculator.